And now a word about electronegativity, a number that describes a tendency of an atom to draw a shared pair of electrons towards itself. So for instance, when looking at the bond of hydrogen and fluorine, there's two electrons that are shared in between the two atoms, and instead of the electrons spending time evenly, the electrons are more likely to spend time near the fluorine. This is a relative scale from 0, in theory, up to 4, fluorine having the highest value, and the higher the number, the better the atom is at hogging electrons. This is only used, or we should only use it, to describe bonded atoms, not individual atoms. We're not going to use it when we're describing ionization energies. We're not going to use it in ionic bonding, only for covalent bonding. It's not a measured number, but instead a calculated number. And so you should notice from this chart that ionization energy increases across the periodic table and up the periodic table, hence up and to the right. Notice I've left metals off. They do have values, but because we're only going to use electronegativity when we're considering covalent bonding, have no need for these metallic values. So some rules to guide you when deciding what connects to what when you're building your Lewis structures. Sometimes the order listed may help. The central atom is often written first, certainly not in the case of water, which I suppose we could write as OH2, but nobody does, so we're not going to start. Also, and not true in the case of water, the lesser electronegative atom is often the central atom. Hydrogens and fluorines are terminal. That doesn't mean that it's going to die. It means on the outside of molecules. And here's a big one. Oxygens do not bond together, except of course in the molecule O2, and except if you're told the molecule is a peroxide molecule. Then the oxygens will bond together, but generally oxygens, you do not want to connect them in your Lewis structures. Carbons love to bond together. Again, love. They don't really love anything, but they'll be on the inside and not terminal atoms, and this is done as a way to avoid unshared pairs. We'll look later at formal charge that will explain that. Here's an acronym to help us. If we're building a carbon-based compound, we'll find hydrogens will have 1 bond generally, oxygens 2, though not always, nitrogens 3 bonds, and carbon 4. These 3 bonds could be a triple bond, or it could be 3 singles, or this could be a double and 2 singles. And up above, this is representing unshared pairs that generally form 2 for oxygen and 1 for nitrogen. Lewis structures for polyatomic ions. Now again, we're not going to concern ourselves with the magnesium sulfite, magnesium having transferred perhaps 2 electrons to sulfate, but instead we're just going to look at the sulfite itself, inside of which we find covalent bonding. So we need to add our valence electrons, and you'll find sulfur with 6 valence electrons as well as oxygen. So certainly that's 6 plus 6 times 3. And let's not forget that we need 2 extra electrons because of the 2- charge on the ion, for a total of 26 electrons, 13 lines. So we'll put the sulfur in the middle with 3 oxygens around it and fill in with the rest of the unshared pairs. I'm allowed to have 13 lines, so I've got 3, 6, 9, 12, and the 13th can complete the octet on the sulfur, and we'll put that in square brackets showing our 2- charge outside. This is a way to distinguish somebody looking at your Lewis structure and knowing that this is sulfite, the ion, not SO3, the molecule, the neutral molecule. On to hydroxide, 6 plus 1 plus the extra 1 electron due to the charge, for a total of 8 electrons. Not a lot of magic with that. Oxygen bonded to hydrogen. Let's put our brackets around it, and so I can have 4 lines. I've used 1, 2, 3, 4, satisfying the octet for the oxygen, and of course remembering that hydrogen only will have 2 electrons near it. That will be a bond, and never any unshared pairs around the hydrogen. Now on to ammonium ion, nitrogen with its 5 valence electrons plus 4 from the hydrogens, and then this time the positive charge means we have to lose an electron for a total again of 8 electrons, 4 lines. Nitrogen in the middle, 4 hydrogens around it. This is pretty analogous to the methane CH4 molecule that we built before, which does not have a charge, but to indicate that this is a polyatomic ion, of course, we want to go with our square brackets and the positive charge outside. Then our bromide ion. Remember, bromine has 7 valence electrons plus 6 from the oxygen plus the 1 added electron due to the charge for a total of 20 electrons, 10 lines. Again, keeping the oxygens from bonding to one another, we'll put the bromine, the less electronegative atom, in the middle, put our square brackets around with our minus charge outside, and fill in. I can have 10 lines total. I've used 2, 3, 4, 5, 6, 7, 8, 9, 10 for bromide. So carbonate with its 4 electrons plus 6 times 3 plus the 2 extra electrons for a total of 24 electrons. Carbon in the middle, 3 oxygens around it. We'll put our square brackets to get that out of the way. And so I have 12 lines available. I've used 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And my oxygen, use them all up. I can't just come and put in the 13th because I do not have 13 available lines. Perhaps you've put your 12th electron pair there, and then of course your carbon is coming up without an octet. Remember, when we come up short on the number of electrons to distribute so that every atom can have an octet, we need to use a double bond. And so I'm going to erase one of these and instead put a double bond in between, and now each atom, the carbon in the middle, will have an octet, and each oxygen will have an octet. Now we'll try nitrite. 5 electrons on the nitrogen, 6 times 2 plus 1 extra electron, giving us 18 electrons. That's 9 lines, putting the nitrogen in the middle and the square brackets with the 1 minus charge. We now have used 2 of our 9 lines, 3, 4, 5, 6, 7, 8, 9. That looks great from a symmetrical point of view, but you can see that your nitrogen in the middle does not have an octet. And again, perhaps you may have put your electrons all around the nitrogen, but you do see that of course your oxygen does not have an octet. Either way, we'll need to erase one of those unshared pairs and make a double bond to satisfy the octet for each atom and only use up 18 electrons. Next we'll try, this is formaldehyde, 1 electron times 2 plus 4 plus 6 for a total of 12 electrons. Now the order that they are arranged would imply that we maybe would want to put hydrogen attached to carbon with another hydrogen attached and then an oxygen. We've used up 3 of the 6 lines available, and so 3, 4, 5, 6. You can see that this oxygen on the end, or perhaps you did give that oxygen on the end all of the pairs, and then you can see that the carbon in the middle does not have an octet. That of course again means that we need a double bond, so I'll erase one of those pairs and we'll put a double bond in between. And lastly, sulfur dioxide, sulfur with 6 plus 6 times 2 18 electrons. Putting the sulfur in the middle, it's less electronegative. The oxygen's not bonding to each other on either side. I've got 9 lines available. Again, 2, 3, 4, 5, 6, 7, 8, 9. You can see the sulfur in the middle coming up short. And so the way to solve that problem will be with a double bond, producing each atom, the oxygen on the end, the sulfur in the middle, the oxygen on this end, all having octets. Of course, it doesn't matter on which side of the molecule you produce a double bond.